Okay, we can get started now. So welcome to Edge Compute Low Latency team number 1. We swapped with our Cisco colleagues so that they could go first and we came second. And this has been a fun collaboration between 5 vendors. So that's the whole thing. And whatever we're showing on the slideware is also in hardware available today to the left. So Druid has graciously hosted it in their booth. So we'll walk through what was it that we did today that we're bringing to the table. So I'd just like to introduce my co-presenters. If you don't mind, my name is Ali Shah. I'm with Nokia. And my co-presenters include?
I'm Tim Godfrey with EPRI. I lead our telecommunications research program at ICT.
My name is Mitch Rapard. I'm with PaloAlto Networks, cybersecurity company, and we used our NGFW for this effort.
Yeah, and good morning, Matthew Brandis with Druid Software. So we're running the private core network, the EPC, for the demo.
Thank you. And so when we made the submission, we did it together with EPRI and Matt. And then Matt, we brought in PaloAlto to the party. And then by nature of the device requirements, Cisco and BEC got engaged to help us out with devices. So you can see there's a lot of moving parts coming together. So just to talk about it, we're going to set up the thing between me and Tim. We'll set up what is edge compute. What are we trying to solve here? I'm going to say a few words, and then Tim's going to add some color. So we're looking at a use case where edge compute and low latency becomes very important. It's not the only use case. This is just the beginning. But the question on the top of everybody's mind is, how can you distribute the compute and lower the latency? And so we took the distribution transfer tip, working with EPRI and Tim. Tell us more about this use case.
Thank you, Ali. Yeah, the direct transfer trip use case is important for DER integration. And we at EPRI have been studying the challenges of achieving sufficiently low latency and reliability over cellular networks to support integration of new solar and other DER sites into distribution networks. That has been found as a challenge for commercial cellular to meet the latency requirements. The specific numbers are unique to every particular distribution feeder, the number of kilowatts or megawatts of energy from the DER site. But in general, the situation is the utility does an analysis of a site that wants to come onto their network and be interconnected. They determine what type of protection will be necessary, and from the characteristics of the DER equipment and the feeder that they're interconnecting to, they'll come up with a protection scheme, often involving direct transfer trip, and that will lead to a latency number. And often that will be found, that number cannot be met reliably by commercial cellular, so the site owners are required to install fiber, which is very expensive, especially in rural areas where there's no infrastructure. So that can often prevent the DER site from being installed. So our research over the past several years at EPRI has looked at different cases of DER for anti-islanding protection and for fault protection for these DER sites and the communication requirements around them. And we have done testing and analysis on commercial cellular, private LTE, private 5G, commercial 5G, NSA, SA, all the different options to more deeply understand this in the specific use case. So here we've shown the example of a simple scenario where we have a DTT transmitters that are able to operate a relay somewhere in the middle of a feeder and then also at the DER site at the right. And putting it in the context of the previous presentation, this is east to west or edge computing, edge communication. We're not necessarily involving anything at a central site. The DTT messages go from the relays either in the substation or out on the feeder. So it's an east to west type communication. But we in this work have pushed the limits on the latency and reduced it down to relatively low levels by using 5G. And we'll get into the details of what we accomplished, but just around the use case, it's all about being able to leverage the capabilities of 5G in particular that offer new lower latency that has been unachievable with other technologies beforehand. So, Ali?
Thank you. So summarize, what are we going to show you? Going back to the screen, as Tim said, what's the edge? We're going to define the edge. The edge has many definitions. But what can you do at the edge? So we already have a RAN site at the edge, the RR edge, the BBU. We can also put a core at the edge. Matt will talk about that from Druid. We can put a firewall there for security applications. And then last but not the least, we have some controllers, RTAC controllers, for a distribution automation application, in this case, DTT. They're at the edge. There are two latencies we're measuring. One is it from the 5G to the edge. The other is from 5G to 5G. And guess what? Which latency will be lower? Can you guess? So that's the next slide. Just hang on there, don't leave us. Okay, so this was the setup which, thanks to Tim's support, we were able to do. A few words on what is a goose message, Tim?
Thank you. Yeah, their direct transfer trip use case can be accomplished with different types of signaling and protocol, but one that has been commonly used and adopted by multiple utilities in the US has been to adopt the IEC 61850 standard, and in particular, what's called the goose message, which originated in substations. Goose stands for generic object-oriented substation enhancements. So that type of a message can be applied in a distribution context for the direct transfer trip use case. We use the Schweitzer RTAC to generate and receive these goose messages, so they're exactly in the format that they would be used in the real world. We've simplified the coding on the RTACs just to take a contact closure on the transmitter. When the contact closes, it sends the message, and then the receiving one will activate a relay to give the end-to-end response. In the real world, a much more complex protection scheme would be programmed in, and the messages could be generated from relays and not the RTAC directly. But we use their software, set this up in a simple scheme to provide the contact closure from one to the other through the network, and that gave us a platform for measuring actual performance over our 5G network using real-world 61850 goose messages.
So you now got the setup. Goose message. Goose is not about turkey or goose. It's a message. And what is it? You have to make it move fast. It's about latency. The quicker you get it, the better you can protect assets. And that was the problem statement we got from EPRI, who does research on this, one of the premier research organizations when it comes to electrical power. Thank you, Tim. So now, how did we set it up? And this is where our Druid coils helped us with a solution. Matt.
Yeah, so the foundation of any cellular network is really going to be the packet core. At the end of the day, the core is what the radio terminates against. It's what the UE's anchor point is. It's the gateway into the network. And traditional thinking has, cores located in a centralized data center, right? You've got RDCs back in our Sprint days. We had regional data centers, putting the cores all the way up there. Well, that has a certain use case. But the beauty of Ramus and Druid Software's private core network, it's purpose-built for private cellular networks. And we can push it all the way down to the edge, as close to the edge as you want. As Ali mentioned, we've got a full CBRS network in our booth today with all live. It's broadcasting live with real devices. And so, you can do the cups thing. There's a lot of talk about offloading user plane at the edge, but still doing cups at a central core. Well, that works, and we can support that. But what happens when you lose that connectivity to the centralized core for that? So why not put the core all the way to the edge or as close to the edge on a small footprint as possible, which we can support? Well, then the question becomes, well, how do you manage that? I don't want to manage 50 cores, right? That becomes a management nightmare, right? So we have what's called the distributed network manager, where you deploy these full cores, gateways, all the way to the edge, but then we manage those through a single pane of glass called the DNM, the distributed network manager. So you can manage the devices, you manage KPIs, faults, the configuration. It stays standard. It's not part of the call path. So if there is a hurricane that disconnects that site from the DNM, that site continues to run autonomously just fine with no issues at all. So yeah, so that's what Ramus Core is all about.
Thanks, Matt. That was a very concise overview. And now we're going to talk about the security component where Palo Alto enriched it with a firewall. Mitch.
Yeah, so we used a next generation firewall, or NGFW, to do kind of two things. One, provide the connectivity. So the radios are actually connecting into that, the RAN is, as is the core. And so we can operate in layer 2 or layer 3 mode. We kind of did a mixture in this project. And then we also wanted to use it for security and visibility. So we have a saying that, in the security industry, you can't protect, but you can't see. So when we watch packets fly across the network, the whole point of a next-gen firewall is to identify exactly what protocol or what application that packet is or what that traffic is. And so the firewall is doing that all the time. That means it's doing layer 7 inspection. It's using heuristics as well to identify the applications on the network. The other thing that we're doing is allowing for zero trust. So zero trust is a very, very important concept in security environments. The idea behind zero trust is that we want to know for every single flow on the network what that flow is, what it represents, which application it is, and if we don't know, we really don't want to allow it, right? So we want to block that. That's called implicit trust, so which is the enemy of zero trust. So the goal in this architecture and the goal in this project was to make sure that we had policies that said, okay, we're going to allow only the relevant protocols that we expect to see on this network. And by the way, that included mobile protocols like GTP, SCTP, and that included IPsec, which is used for the overlay network, as well as DNS and various other protocols. So we could see all of that on the firewall as that traffic traversed the solution. The other thing we want to do is make sure that it's secure. So if you're familiar with next generation firewall, typically they have components like IPS and IDS built into them. So we can look at the traffic and make sure there's no exploit attempt that's going on across the network. We can look for if there's firmware updates or downloads, we can make sure there's no malware as well on the network. So we're watching this traffic all the time. We're safely enabling the protocols that should be on the network, and then we're looking into the payload of those protocols and those applications to make sure that that is valid traffic and there's no malicious traffic in that communication that's happening. The other thing we do that's very unique at PaloAlto Networks is we provide visibility of the device identifiers of the mobile devices that are on the network. So in a mobile environment, we have things like MZs and IMEIs. These are the kind of the software and hardware components of the actual mobile device. So in our case, that would be the IR1101, which is a cellular router. The PaloAlto Networks firewall has the ability to identify what those are, and you can create policy based on that. So you can say, hey, this mobile identity can talk to this, this application, or vice versa. Maybe it can't talk to this application. So your policies can be very granular. The IP address can change, doesn't matter. We'll keep track of what the MZ and the IMEI is, and we'll allow for policy based on that. And so this is extremely important as well for zero trust. We want to make sure that in zero trust, we know as much as we can about every flow. I want to know the application. I want to know the 5-tuple. I want to know the network identifier. I might even want to know the make and the model of the device as well, right? So other characteristics too. So all of that was turned on in this environment to make sure that we had as much visibility as possible. We secured the network as well. So you can see there we talk about different kinds of attacks that could have happened. We didn't get time to simulate attacks. I would have loved to have done that, but we focused more on the latency. But these could be DOS attacks. These could be signaling that's malformed. So I mentioned SCTP. That's a signaling protocol that's used from the radio to the core. One popular attack vector is to use malformed SCTP messages to try to interfere with the packet core. So we would detect that and block that. There's lots of different things that we can do above and beyond that visibility that I mentioned. And the last thing I'll mention on this slide is I think you guys all know there's kind of two categories of threats. There's threats that we know about, that we've heard about, maybe we've read in the trade rags, that's known threats. And those are not that difficult to stop, right? But you want to make sure you stop them. The really hard ones to stop are the unknown threats. The threats that are 0 days that we've never seen before. And so PaloAlto Networks spends a lot of time and energy to make sure that we can detect unknown threats, so that 0 day. And we use machine learning on the actual NGFW, the firewall, to, at line rate, watch those messages, watch those protocols, and look for threats that are embedded in there that have never been seen before. So that was kind of what we brought to the table, and that was some of the capabilities of our firewall. I think the next slide will talk about what we observed as we were testing. We are a zone-based firewall, so this is a little bit in the weeds, but for the geeks out there like me that want to know this, we did come up with 4 zones that we used. On the radio side, we kind of had 2. One zone was facing towards the RAN, and one zone was facing towards the core. And then we also had zones for the N6 interface, which is the LAN side of the packet core, if you will. And so we use those zones to create policies, but then we also saw that MZ and the IMEI that I mentioned a moment ago as well in the traffic logs. You see that there at the bottom, that screenshot. That's a screenshot of our traffic log where you see the traffic coming in. You can see that it's it's IPsec for one of them, and then the second row is ping. Maybe you can't see that from where you're standing, but it's different protocols, not just ports and IP addresses. It has that too, but it has way more than that as well. And so we based our policies based on this. So our policies were looking at the relevant applications, and we did as much as we could to make really granular policies to apply to zero trust principles to make sure that the security was as effective as possible. The last thing I forgot to mention on the last slide, Druid and PaloAlto Networks have a tech partnership together that we did a while ago. And so that technology partnership enabled that visibility into the MZ and the IMEI that I mentioned a moment ago. So they were feeding us that information from their packet core straight to the firewall, so the firewall would know what the IMEI and the MZs were for all the devices on the network. And so it all came together because of the tech partnership that we had done before, and then just kind of implementing zero trust policies.
So now we go to the next part, and for that I have to ask you a question. So you heard what Goose is. Is Goose layer 2 or layer 3? Is it the IP level or is it layer 2? Layer 2. So now we have a problem. How do you get a layer 2 protocol onto the network? LTE for 5G network needs an IP packet. You can't put a layer 2 there. So what we do is enter devices. So in this case, we had 2 partners. One is Cisco. Dan Mady helped us out. And of course, BEC, if BEC is here. But the way then we configured the Cisco IR1101, which you also saw in the previous presentation, where it's the edge compute itself. So there are different definitions of edge compute. That's the message here. We put the RTAC, which creates the Goose message, the core, and the firewall on the edge with our RAN. That's our definition. There's another definition where the device itself could be the edge. You saw in Dan's presentation from Cisco. All these are all good, valid definitions. Nobody's right, wrong. But what we did is then we took IR11 and used it in a hub and spoke model and all configured it so that it could take the packet, the Goose packet from the RTAC, encapsulate it, and then transmit it over 5G. And that's the whole story. So now you got the architectural setup. Any questions before we now get into the test results? Or any comments from anybody? Have we got you engaged? Everybody following? Okay. So now, what is edge compute and low latency? This is where the Nokia secret sauce comes in, which is again all based on open standards. Nothing secret. These are all specifications of 3GPP. So edge can be, in our definition, if you want to lower the latency, you just take the compute and whatever you want to do closer to the site. If the core is sitting hundreds of miles away, that's going to introduce some latency, not huge. So every millisecond of improvement counts in the world of extreme energy consumption driven by AI/ML, driven by electrical vehicle charging. You need to improve latency continuously. So what we employed is a very simple trick, which 5G gives you. If you look at the bottom right, 5G allows you to tinker with the frame structure, something called subcarrier spacing. This is getting, oh my gosh, too technical now. So you can go, in the ideal world, if the FDD frame today can do 15 milliseconds of one way, latency is one directional, then if you can put a CBRS TDD onto it with a 30 kilohertz subcarrier spacing, you can reduce it because of just that smaller symbol size. That's the logic. This is a 5G concept. It's not the only trick in our toolbox. It's a beginning of a journey where we're trying to take it down, down, down to milliseconds over the coming years. A lot of potential. So that's the technique we used. And again, we're measuring 2 things, a 5G to 5G and a 5G to edge. And what is the definition of the edge in 3GPP world? Can anybody guess? Mitch and Matt talked about it. Can anybody tell me what that edge is? It's called the N6 interface, which comes from the Druid core. And that's what we're calling the edge. So everybody now knows what we're measuring in terms of latency. The only limitation is, can we load it up and convert real-world conditions? So we thinking about bringing 6 vendors together, we didn't really put our energy into creating real-world conditions for this time. We just focused on the idealistic conditions. So what are you going to see? You're going to see in the latency 10 millisecond numbers. That's what I'm setting you up for. If it's 5G to the edge. But if it's 5G to 5G, you'll see 20. And this is where my colleague then helped me build some very nice slides. So let's get started. This is the network topology. You're welcome to join us. We've hidden it all from view, but it's sitting in front of you, hidden from just to make it not look ugly. It's an experimental setup. You'll see what it looks like. So this is how it all come together. Again, making it all work, which is the spirit of the Plugfest. And then, as I said, we measured the results. We're seeing the numbers that I mentioned, but we'll go deeper into these numbers a little bit. Samir, if you want to add some commentary, you're more than welcome to. And so, by the way, how are we doing on time? Time-wise, we're OK. So we have time for questions. Stop me if you want. So now this is the 5G air interface. What are we going to see? We're going to see the RTAC in the bottom, encapsulate the message over Cisco for the device. So the Goose message is now getting encapsulated, and they've got a whole addressing scheme there where Cisco deploys VXLANs. There are different methods, but that's one of them. And then we transmit it over the air interface, so our Nokia radio takes it, and then the firewall here is also acting as a switch, by the way. So we use it for dual purpose. It's going to the Ramus core. And then if at the edge you have another IR11 and then another RTAC. So you'll see that message flow. And then this is where what we did is we just did the benchmarking. How much does it take? So there's a clicker there. There's a button there. You can click and you'll see the latency come up. But this was just to capture. We used Wireshark in this case to capture the latency. And so this is the flow from 5G to edge. This is how the traffic is going. Why at the edge again? Because the edge is sitting, the N6 interface is sitting at the core. Okay, so we do need to get the addressing right. Dan from Cisco really helped us here to get everything. So this is the setup. What are the results? So this is the average is what? And what was the theory I told you? The theory was in ideal conditions, you'll see 10 millisecond. Tim, you want to talk about 10 millisecond and the significance of that?
Well, yeah, it's significantly lower than what has been achievable to date. And it's a aspirational goal for enabling direct transfer trip, anti-islanding, and even more challenging use cases such as high density coordination and distribution that are today limited to fiber. So a huge opportunity for cost savings and ability to use our wireless networks for additional use cases, because the many use cases are not latency sensitive and are easily handled, but this one area of latency is one that the industry has seen as a challenge, and we've been putting a lot of effort into solving it. And here this shows a definite step in the right direction through use of 5G.
Thank you, Tim. So now we move to the next one, and then of course we have the ping and everything. Anybody who's a geek who wants to get into the bits and bytes, we have the geeks for you. So if you want to stay at the leadership level, we've got that message, but we have all the stuff for anybody who wants to talk about it. And nobody has on the floor put together a security story, a core story, the Goose story, and the radio story in one. You have the whole team. We can take any question. We can tear apart for you. We can simulate scenarios for you if you want, on the fly, on the shore floor today. No other team has done that, by the way. So with that, now let's go to device to device. Why is device to device also interesting? Because architecturally, you can't squeeze in the core in every location. But if you were able to, and you can talk to Matt about that if it's possible, you still need to have 5G to 5G, because some places you'll still have to cover with 5G. And then this is the latency. You're going back to the core, but then you go back over the air interface to the other Cisco router, but now it's not connected to the edge, it's connected to another 5G router. So in this case, Cisco is not being used as the edge device, but it's being used as a router with a 5G modem in it. And so what is the expected latency you're going to see here now? Can anybody guess? Is it 5 millisecond or 20 millisecond? 20. So Romin says 20. Anybody going different? Greg, what do you want to say? 5 or 10? So 10 millisecond with 5G to edge. So let's see the results. 5G to 5G is 18.7 millisecond average. Okay, so as we had expected, these are idealistic conditions. It gets a little worse than that in the real world, but not very far off. But this is a tremendous improvement. So we also have an LTE demo, by the way, with a core sitting far away in Dallas. And you can go there and check the latency on that one. Of course, it's going to be much higher. So that's the point there. If you play with the architecture, if you play with the technology, go from 4G to 5G, there are some improvements possible, and there's a lot of work to be done now to the next steps. And so to summarize, 5G to 5G is about twice the latency about 5G to edge. Again, the most important thing isn't the numbers, but it's the fact that we were able to work around these companies. I also should mention WWT, who was working with Cisco to give us the devices. So all mentioned, and Mike Robinson also was a big influencer on our thinking process here. So again, that's the net conclusion. It's just the beginning of many years of work. And by the way, Nokia has a 5G network up and running as we speak. We'll talk later about who that is if you want to stop by. So I had a 1-minute video just to show all the goof-ups and all the work we had to do. This may not be the best, but let me at least, what's the way I click on this one? Okay, this is just showing, thanks to Tim, we were able to, so this is a messy stuff, but it says what geeks do. This is our geek land now, okay? So not everything has to be marketing land. This is the geek story. This is how we worked, connected everything. And you're more than welcome. The same thing we're showing on the video is available. So I'm going to start getting you to think about, this is distribution transfer trip is just one use case. Each one of you has to come up with another use case where latency is important. So anybody going to go first while we're going through the video? What's the other use case where you need lower latency, folks? I've got 4, by the way, in my slides. A little bit, as you can see, it's not the most marketing. So again, what can you do with these architectures? So we put this slide in the end. There are different architectures out there. This is not an architectural discussion. It's about getting results. Lower the latency. If there's an economic point, you need to talk about that. We can go into detail. Each one of us can give you their view, and there'll be a diversity of views. That is good. That is not bad. It's good that using open standards, we can come up with different architectural formulations. I'm going to now, before my last slide, and then we'll open it up for more comments and discussion. So here are the 4 ideas I have where edge compute becomes very important, and they're already being implemented. So our Antrix colleagues have a whole discussion on AMI 2.0 and edge compute being relevant there. You can go to the AMI discussion. Why? Because latency in AMI 2.0 is also important. It's not into the millisecond level, but you need guaranteed latency. So there's fall-in conductor protection. Our West Coast utilities really need that. Latency is everything. You don't want a power line to cause a forest fire. You want to de-energize it. Latency is critical there. So our California utilities really focused on that. Flizzr, we have that actually in our demo for location identification service restoration. We're doing it with LTE today, IP over IPVLS, but that's another one where latency. And then high density coordination is a different problem statement. It's coordinating between different reclosers, making sure they're coordinated when you turn them off or turn them on. These are just simple examples. Any other ideas? Anybody who, Tim, you want to talk about any other use case? The big ones are these four. There are some more out there, some more, each vendor has their own. So that this is just the beginning. We have just scratched the surface. I'd like to open it up for any questions from the audience, please. And yes, sir.
Can you talk about the practicality of being able to do this on commercial networks versus private networks?
So the question is, how practical is it to implement edge compute on a commercial network? And you mean with say, a Verizon or an AT&T. So first of all, a Verizon or an AT&T will strictly control the architecture of their network. They own everything, and they will only give you a SIM card. So, of course, I'm now not going to go into detail. I have to be respectful. Verizon is also here, and T-Mobile is also here. But they have their network integrity in mind. So when you try to take this, you're not able to control the latency because they will have to decide the architecture. It's their constraint, and it's an engineering constraint. Where you own the network, you have more flexibility. But with that, there may be another view to that. Tim, do you agree with that? Is it easy to achieve that?
I mean, all of the commercial carriers, as they evolve in their 5G offerings, are finding ways to differentiate and offer semi-private, they may call it a private network operating in their spectrum, or various levels of differentiation. The whole concept of network slicing that's introduced by 5G and 3GPP is just beginning to come out in early deployments on commercial networks. And the holy grail, or the ultimate goal, is what's called URLLC, ultra reliable low latency communication, which is something that's defined in the 5G standards, but not yet implemented in commercial products. When that arrives, that'll bring a new realm of capability and further reduce latency on both private and commercial networks. But I think, as Ali is saying, the ability of private networks today, there's much more flexibility in the definition of the architecture and the control. You talked about the framing, the subcarrier spacing, all those things are in your control on a private network, but they have to be reconciled with the needs of many subscribers on a commercial network.
Yeah, so Samir, you had another comment to make on that question?
Samir from Nokia. I just wanted to add that with the CSP setup, your traffic nature is much more different and diverse than what you have on the private network for utilities, right? Here you have the device mix is not that varying, right? And also the services and the traffic is more homogeneous, so you can optimize for a specific traffic profile and traffic service, so you have more configuration control over your DSCP and quality of service, because again, you're just optimizing for a specific device mix and specific service.
The question, of course, is a very detailed question. We can't do just in 30 seconds, but we tried our best. Yes, network slicing will be a big enabler. At the same time, there are much more concerns of the movement to private wireless. Any other questions, please? Ram.
My name is Ram Swaminathan. I'm a consultant at Burns & McDonnell, and I have actually, the whole concept of edge compute was to move the user plane, not the whole core, to the edge. Now, not that a use case could not have a whole core at the edge, but when a utility has multiple data centers with head ends at various locations, and geo-redundancy and resiliency is also of critical nature. And you're building a core for more than a dozen use cases. How would you build out when you're deploying a core at every substation while you have to manage other head ends? Sometimes same IEDs are communicating to each other at the edge, but they're also communicating to their central systems.
So the question around the architecture, there are different opinions. Nokia will have a different, but because Matt and we've collaborated, we're going to listen to Matt's opinion on this.
Yeah, I mean, I think it comes down to a balance, right? I mean, you may not need a full core at every substation, but the beauty of Remus is we can integrate in with those enterprise networks very simply. So we talked about the 5G to the N6. So if that's a connectivity over a backhaul to a 5G, you just have to balance how far close to the edge, right? I mean, you're not maybe going to put a full core at a substation that's got 2 devices. Probably doesn't make sense. But if you've got, we were just having this conversation with a customer, if you've got full cores at an edge that's got 100 devices that need to communicate with each other, you still have that ability to route, back into a centralized core like you're talking about. Yeah.
Please.
Yeah, I guess we can agree that it comes down to a balance, like you mentioned, but it would also come down to the utility and their use cases and what makes the most optimal sense in deploying such architecture. So, yeah, that was my comment I wanted to make. Thank you.
Thanks, Ram. And yes, as we said, Druid believes the localized core. Nokia, of course, has a more localized UPF function. So they're different philosophies. Samer, you have any comments there?
I thought it was a very interesting question, and the core function now, I can't speak more than what Matt can say, but the core functions are mostly software functions. So if you're implementing the user plane function or the AMF or other functions, it's, again, software components running on that hardware. But again, the nature of the devices for the utility use cases is stationary. And as we can see in our demo, that sending device or the publisher is sending its messages at certain periodicity, and it's always in connected mode. So it doesn't need that control plane maybe messaging that often. So you establish a connection, you're latched on the network, you're good to go. The rest is user plane interaction. So yeah, it makes sense to have maybe that user plane, or that's the idea why the user plane makes more sense or more impact when it's towards the edge. But again, since from Droid side, since it's small form factor and it just fits there, so you're getting some optimization on the control plane and user plane latency. But yeah, user plane might be more impactful in that.
Ram, let's use.
Sorry, this will be the last thing I'll say. No, I also wanted to say that, availability is also huge for when you own a private network. And I guess, again, with all respect to all present here, we're talking private LTE for utility, and they want to be able to control all aspects of it. And then, of course, if we need to deploy a core at a substation level, then we need to also consider for redundancy and resiliency as well. So that sometimes doubles your deployment. True? Yeah. So how much are you going to put in there is the question.
Point taken. So the real, and that's why we call this, the beauty of the Plugfest this time has been that there is always a business decision maker and there's a technical. This Plugfest round has allowed the business translators to come to the fore, because now we have done all the testing 3 months in advance. All of us are more like business translators. Each one of us can sit down and write down the TCO model for you. That's the discussion. And so it's not really the testing itself, which is important, by the way. You need to make sure it works. But what TCO model is going to be optimum, and each one can spend hours on that topic, Ram. And with you, and you yourself are very educated on that. Any other questions, please? That was an excellent set of questions. Please. Any other questions on? So I think we want to just start wrapping up and talk about it. Let me go back to the first slide, setting it up on DTT. So distribution transfer trip is a protection mechanism in a distribution network. What problem we're solving there is that if there is a fault, and look at the DER on the right, the distributed energy resource, that's a solar array. It's pumping in voltage into the system. If there is a fault somewhere in the relays and you do not disconnect the DER, you have got what we call an islanding problem. It's very dangerous. So if a technician goes there and touches something and it is energized and there's no place for the energy to go, it can be life-threatening. So this is a very important use case. The requirement on latency isn't in the tens of milliseconds. Tim can give me a correction, but it's around the 100 millisecond mark. But it depends on various factors. But the lower we can get it, the better, the more safety at the end of the day. Because maybe a tenth of a millisecond is a matter of life and death. That's the importance here of this use case. And so the novelty of what we did is we did it for the first time on the show floor with 5G. That's the novelty. And the other piece is, again, I want to have each of the team members, we have a few minutes if you want to speak a few words, and we wrap up. Matt?
I'm good. Matt, I'm good. No, just to recap, it was a collaborative effort, as Ali mentioned, and I just want to reemphasize the importance of the visibility that we were able to bring to the table. I think that was super important for understanding exactly what's on the networking, making sure it's clean, it's only what you expect to be on the network.
Yeah, this area of low latency communication for DER integration and other use cases is one of the remaining challenges for the industry in applying private and commercial LTE in utility operations in their field area networks. So we will continue to work on understanding the capabilities of networks, how to optimize 4G and 5G networks, and support more of these applications wirelessly instead of having to install fiber, which is an opportunity for great cost savings. So that's work that will be continuing in our EPRI research in the coming years.
Thanks, Matt from Druid, Mitch from PaloAlto, Tim Godfrey from EPRI, and big shout out also to our other device partners, Dan Mady from Cisco and WWT Mike Robinson, and then our BEC colleagues, Jensen. And yeah, thanks for providing the devices and helping us make it a successful collaboration. We look forward to the floor. You're welcome to join us at the booth. Druid has graciously offered us some space to showcase it. It's just next doors. Thank you so much.